So the first one that we want to talk about is we want to talk about alpha decays. And so we have to go through the details, but the most important thing here is the applications of radiations. Okay, so we got to go through these details, but the coolest part, without any doubt, is the applications. So let's go through the alpha decays. And the alpha decays is the yellow band. So if I go and I look at these guys, I really need this thing right here. Right, I need my table here, and I want to look at this guy right here. And when I see the yellow band, you could see that there's really, you could see that I have this guy right here. And then there's some others that are spread out. And then you can see that there's also somewhere around here. So most of the yellow ones occur in these regions. So what you're seeing here is that, yes, this is the region of alpha decays. And that's what we're talking about right there. So many of these you could see. So let's be careful here. Okay, I want to be careful here. So I want to come in here and I'm going to say, remember 82 right there. This is the lead nucleus, right? That's the last stable nuclei, lead. So when you look at lead here, many of these in the yellow are much heavier than lead. So what you're finding here is that many of the very heavy nuclei are unstable And it turns out that the alpha decays how do I say that? Let me be careful how I want to say this here. Many of these heavy nuclei are unstable. The alpha decays are the fastest way to stability. Ooh, that stability does not look very good. Let me try that again. And what I mean by this is that when you look at decays, there's a saying here, and it goes like, all systems always move from high energy to low energy states. And this is very, very true with the unstable particles. And so what I'm saying here is that if I have a nuclei, that these nuclei are going to decay. So that means all unstable nuclei will decay until they reach the black line of stability. Okay, they're going to try to go to the black line of stability. That's always the case. So let's talk about alpha. So alpha tells us that if you have very heavy nuclei and they're unstable, and that's these yellow regions, these guys always, almost always go alpha decay. Why? Because it's the fastest way to stability. So now let's go look at this thing a little bit more careful. So alpha decays have their radiation particles called alpha particles. And that kind of seems obvious, right? Alpha decay and alpha particles. Well, it turns out that when you go back to Rutherford, he didn't know what an alpha particle was. That's why he was using it to try to find out about the nucleus. So if you really look at the details of an alpha particle is a helium ion. And a helium ion, this means here is that it has no electrons. It's a helium ion. So when you look at the alpha particle, so what he calls an alpha is really a helium nuclei without electrons. So when I look at it, it looks something like this here. It has 2 protons and it has 2 neutrons. So when I look at this, what we say here, it's 4,2 helium, but because it has no electrons, it's not neutral. This is what we call an alpha right here. This is an alpha particle. You know, if Rutherford had known that, he probably would have said, hey, it's just a helium nuclei. But he didn't know about this. So just to remind you here, a helium atom is neutral, while a alpha particle is charged, is positively charged. That's the big difference. So the question is, how do alpha particles and unstable nuclei work? So here we go. So how do I want to write this here? So question, how does an alpha decay change in unstable nuclei? Right? And that's a big question. Okay, how does it change it? Well, first, what we need to do here is we need to sort of look at what an alpha is in detail. So what we're going to see here is that we should probably write this in 2 steps here. So a alpha particle carries away, maybe I should write that big. It carries away 4 atomic masses and 2 atomic numbers. And what I mean by that is that when you look at an alpha particle, remember, an alpha particle is what? So let's be careful here. I have 4 and 2 for this guy. So you could see right here is that this here, this is 4 atomic masses. And then, of course, this guy is 2 atomic numbers. Right? So in this case, we know that this guy has to be 2 protons and therefore 2 neutrons. And in this case, this is 2 protons. So now, with that in mind, is that we have a reaction equation. So the reaction equation looks like this here. So remember, A equals atomic mass. Z is atomic number. And don't think about this as a formula. Think about this as sort of like a picture. So here we go. So I have an unstable nuclei, and I'm going to call it A, Z, X. And here's my unstable nuclei. And what it's going to do here is it's going to alpha decay. So then I'm going to see an alpha decay. So the first thing that I see here is that with this alpha decay, it emits an alpha. So let's write the details of the alpha. So the alpha then has what? 4, 2. So it carries 4 atomic masses and it carries 2 protons. So what it does here is that this is what's typically called the parent, and then it has daughters. So then I have a new element. So I look at my A and I look at my Z, and then I go, what did the helium carry away? Well, it carried away 4. And it also carried away 2. So then when you're looking at these daughters, let's say we focus on this daughter, what you're seeing here is that it changes it by this way. So this by itself is what we call our reaction equation for alphas. But I don't think of this as a mathematical equation. I think of this as a picture. So if I think about this as a picture, let me move this here just a little bit, okay? Because I want to draw the picture over here to the right here. So if I do this, I'm going to bring this down just a tiny bit. So then here's this guy. And so then when I think about my picture of this decay, here's what I see. What I see here is that I have a nuclei that's unstable. It's this guy. So when I look at this unstable nuclei, it's A, Z, X. So this is my unstable parent nuclei. So then it has daughters. So we got to be careful here. So what you find here is that it literally, you can think about magic if you want. And then what you see here is that all of a sudden, if you know what bewitch is, it instantly changes. So this is spontaneous. It just spontaneously changes. And as it spontaneously changes, it goes into three pieces. There's the daughter. So one of the daughters literally comes out of this thing. So you know what? I'm going to take this spontaneous, I'm going to move it up here because I need the space. Okay, apparently. So from this, magical process, what you see here is that you see a daughter, one of the daughters, that literally suddenly appears. And this daughter does what? We should be careful here. So look at this. This is A minus 4, Z minus 2, Y. So this is one of the daughters. The other daughter is the alpha particle. So when I look at the alpha particle, of course, it has 2 protons, 2 neutrons. So I know that in this case, I have an alpha, which is, of course, 4,2 helium ion. And then the other thing that it does here is that there's a release of energy. And that's the picture that you should have in your mind right there. So I'm going to say this again because I think it's important. And then I want to go in and look at some examples here. So here we go. So again, I'm just going to repeat myself because I think that's important. Alpha decays happen mostly to very heavy nuclei. Okay, to very heavy nuclei. And so that means here is that they have to be heavier than lead. And I would say here is that, why does it happen to very heavy nuclei? And the answer is these radioactive decays use alpha because it's the quickest way to reach stability. And this is the important piece, the quickest way to reach stability.